In this video, I'll give a brief introduction to simple linear regression. That means if you have one dependent variable or outcome variable and one independent variable or predictor, both being continuous, although we'll see later that we can also have predictors that are not continuous. A simple linear regression model takes this form. We have y, which is the outcome variable, some intercept plus some slope times x plus the residual or the error around it. We assume that there is some real line, linear line, straight line between x and y that explains the relationship between x and y, x being your independent variable or your predictor, and y being your outcome variable or your dependent variable. And we assume this relationship is linear, but this error here means that we also assume that the points are not perfectly on the line, they're a bit around it. So your data points are not actually exactly on the line. We don't expect we can fully predict the data that well, but we expect the line will be close to all these data points. So y is the outcome variable, x predictor, or dependent or independent variables. B0 or B0 is the intercept. So that's the height of the line when x equals 0. As the intercept controls, let's say if you have our line here, the intercept controls this distance here. And then the slope controls the change in the line. So how steep is the line? This epsilon is normally distributed error term, which means that it's the deviation from this true line that we don't know. We don't know this true line. We don't know this intercept or this slope. They are true parameters. We assume there's a real line, but we don't actually know these. So we also don't know where the line is. We don't know this deviation from the line. We find this line by minimizing the sum of squared residuals, which means that we're going to try to find a line that is as close as possible to all the points in the data. And you don't have to do that. Jazz will do that for you, but that's the idea behind it. After estimating a line, we write something different. This equation becomes, in a sense, this equation, where we say the height of the line, the predicted value, is the estimated intercept plus the estimated slope times x. This hat here refers to that these are estimated values. They might not be the same as these true parameters, right? So maybe b1 hat equals like 0.002, something very low, and b1 actually equals 0. There is no effect, right? And that's what we're trying to find out using statistical significance testing. Okay, so here I have a line. I have data points. These are my data points. Every animal here scores a certain level of loneliness, a certain level of happiness. And we use Jazz to figure out what is the best fitting linear line. So this line is close to all these data points. Now, when we assess how well the line fits, we will talk about sums of squares. And sums of squares are basically the variation. So if we have a data set, right, you have a normal distribution, we assume the error term is normally distributed in this case. There's a variation, a standard deviation that controls how wide the distribution is. And the sum of squares is actually the only part we really need from that. If we divide sums of squares by n-1, we get variance. We take square root of that, we get a standard deviation. Those numbers are more interpretable, but we don't actually need them because those are just things to, constant things to divide the sum of squares by. And we can do without this square root or without this n-1 if we just want to see how much the variation changes between two models. So that's why we use sums of squares. We have three different types of sums of squares. We have the total sums of squares, which is the sum of square distances from the average. So here we don't take the predictor into account, right? This is simply the average of the outcome variable. And this is the score, so there is no x here, right? The model sums of squares, so here we look at the distance between the line, the height of the line, and the average. And the height of the line is determined by x, because there is a line. And the residual sums of squares, and this is the most important one, this is the one we're actually going to talk about a lot, the deviation from the line. Right? And actually, you might see already that these are actually kind of the same, where this is just a flat line, where there is no prediction. So if x does not predict y, we could say there's a flat line. And it's no different for any level of x. And that would be the mean. That would be the best flat line in that case. So actually, these things are the same. This will be a bit important later on in the course. The way that you can make sense of these numbers is that they basically capture how much uncertainty there is in your data. How much do we not know? How much variation is there? Right, these sample squares are actually very closely related to the standard deviation and the variance. They're basically just the same number, except they're not scaled to a scale that's more interpretable. That doesn't really matter. It's basically the one number that really defines how much variation there is. The total sample squares is your total variation in a variable. So how much uncertainty is there in total? How much do people differ on some score? Right, so maybe you have some people that are very happy, some people that are not happy, and there's a lot of variation in that. This one equals the model sample squares plus the residual sample squares. Which means that basically the total variation is made up of the stuff that can be explained by a model, in this case one predictor, x, and the stuff that cannot be explained. But we want the model sample square to be very high, almost as close as possible as the total sample squares. In that case, our model is really good, and our predictor explains a lot of the variation, a lot of the uncertainty is reduced. It means that we want our residual sample squares actually to be as low as we can, because the lower it is, the better. So let's draw a example. So let's say we have a predictor x, some independent variable, an outcome variable y. And suppose we measure people and we get these scores. Right, so one person, let's say this is 1, 2, 3, 4, 5, etc. This is 1, 2, 3, 4, 5, etc. So this person here scores a 1 on x and a 1 on y. And this person here scores a 2 on x and a 2 on y, etc. Okay, so we have y, say basically the data like a 1, we have a 2, someone scores a 3, someone scores a 4, and maybe not exactly that sequence, right? Maybe it's 3.1, or for example, or 3.9. Doesn't really matter. The idea is that we get different scores, right? These are more. These are not the same, so that means that we get some variation, right? We get a standard deviation that is above 0, or that means also the total sample squares is above 0. It means that if we draw a distribution, the distribution has some spread, some width, right? If we draw a histogram, we don't get the same point over and over again, right? That would mean that everybody has the same score, same level of happiness. That's not the case. There's some variation in there, and that variation is what we're trying to explain. Now in this case, the model, the best fitting line would actually go to all these points here, pretty much exactly. I didn't draw it perfect now, but you can imagine that it goes exactly to these points. And that means that after we take the line into account, there is no variation anymore. The distance on this line is pretty much 0 for every point. That means that after we take x into account, basically we don't have uncertainty. Like now we don't know if someone is high or low. We don't have uncertainty. We know exactly what the y score would be for every person given their x score. So that would mean that the sum of square residuals is 0, drops out. And sum square total equals the model sample square. They're the same thing in this case. That's ideally what we want. Now you're gonna get that exact. You're always gonna get some residual sample squares. It would be really, really weird if you don't. But ideally you want this to be large and this to be small. Now, what is large and what is small? That's a statistical question. And that's something we're going to look at and basically investigate using statistical inference. Now, one thing that we can do, for example, is calculate the r squared, the explained variance, by simply dividing the model sample squares by the total sample squares. Right? If they're the same, then this would be 1. If the model sample squares is 0, means that the model is bad, it would be 0. Basically, it's a percentage between 0 and 1 that says how much of the variance is explained by your model. And we want this to be higher, right? Higher than 0, right? We want the model to explain some variation. Yes, let's look at some graphs. So here you can imagine this is a model where basically we have our happiness score, let's say our predicted happiness score, and we just equal that to the mean. We say, okay, the happiness score for every person is just the mean. Right? Technically, we would write is some intercept and nothing else. That mean would be 15. That means that for every person, we predict a happiness score of 15. That means in this case, loneliness is not doing anything. Right? This line is the same for any level of loneliness. Right? So you can also see this regression here, like the predicted score of age is an intercept plus nothing, right? No slope on loneliness. That's the worst possible model we can make for this variable happiness, because we don't take anything into account. We just take its mean into account. Now we're interested in seeing, okay, what's the total variation in our data? How much do the scores actually differ? If there's no variation, then every person would have the same response as the mean. There would be no differences between here. But there is variation, we see that, right? They're not the same, they have different scores on the happiness scale. So we can calculate that. The one that we can do is we can look for every individual in our data, basically this distance between the mean and their score. Right, so this person is, bird in this case, at a happiness score of 30, like a super happy bird, really happy, great bird, happy, which is much higher than this mean of 15. How much higher? 30 minus 15 equals 15. 15 points higher, exactly. That's what we call the deviance of the line. Now, the annoying thing about this deviance, is that it will also be negative. So for example, this one, this is like 7, I guess, right? So we get 7 minus 15, right? And that is something that is negative. Yeah, it will be less than 0. Now summing positive and negative values will give you basically 0. If we want to calculate an average distance from the mean, we would get 0. So we don't want that. So what we do is we square the deviance. And squaring means we multiply it by itself. So 15 squared equals 15 times 15 equals 225. The nice thing about squaring is that you always will get a positive number. If you multiply a negative number by itself, it will still be positive. So that's nice, because basically the more all these points are away from the line, the higher this number will be, and it will not become lower. Right? If the points are further away from the line, it will just be higher. Right? We could then divide that number by n minus 1 and take a square root to calculate standard deviation, but we don't have to in this case, because this number already is interpretable. Okay, we can do this for this one, which I already highlighted. So 7 minus 15 is minus 8. But yeah, minus 8 times minus 8, right, is a positive number. 64 in this case, right? So minus 8 times minus 8 becomes 64. We do that for every data point. We sum them, then we get our total variation in the data. 1054 points, whatever that is. Right? There's a high number. We could divide by n minus 1, take the square root for the standard deviation, but there's no reason to do that here. Because we want to know, okay, if we now draw a line where we do take loneliness into account, so now we don't do that yet, do we get a better model? Okay, so let's do that. We draw a line. Now we don't just draw any line. We actually draw the lines so that all these distances from the line that we have here are as small as possible. It's called least squares estimation. You don't have to do that. The software does it for you. But basically what you can think of it as thinking, okay, first we try a line here. No, that's not good. Let's try a line here. No, that's not good. Let's try this line. No, that's not good. We keep trying different lines until we get the best possible line. And then afterwards we can no longer improve that line. You can think of it like that. Now from this line, we can do actually the same thing we did here, right? So that's why I drew it like this, to show that it actually is the same. So here we do have a slope and we do take loneliness into account. So the line is not flat, it actually takes loneliness into account as a predictor. And we can look for every point, what's the distance from the line, and square that number to get these square distances.
Right.
For some of them it will actually be further from the mean, like this hamster, but for most it will be much closer by. These are much smaller numbers. So this line works much better. We sum all these distances up, we get the residual sums of squares, which in this case is 443.6. So that means our uncertainty was 1054 points, but now it's 443.6 points when we take loneliness into account as predicted. Well, that's great, right? That's really good. That's like we know much more about the data. Loneliness tells us a lot about happiness. If you take loneliness into account, we understand happiness much better. So that's why we call it a significant predictor. Right? This sum square model is actually just the difference between these two. So how many points did we increase in our prediction, or how many points did we reduce our uncertainty with? And you can see it as summing these square distances between the mean and the line. That's not actually something you really do. Normally the software will just calculate this for you and then compare them, but you can see it like this. Alright, so we have three distances. And here you have all three, right? So you have the red one, this from the mean. Oh, let's say this one here, this from the mean. We have the blue ones, which is from the line, and the purple ones, which is the difference between the mean and the line, right? And that gives us these three values. Now we can use these, we actually only need to use two of them, to get the r squared, the explained variance. In this case, 0.58. So we explained 58% of the uncertainty in our data by taking loneliness into account. Now, this is based on a sample, so we're always going to get something, right? You will basically get some number here, it will never be exactly 0. The question is it actually significantly different from 0? And that's something that we can test, we have a test for, that's something we do. In this case, it's so high that this is very likely significant, but we can actually perform a test to find that out. That's it for this video.